Go ahead.
Okay, go ahead.
Yep.
Can you see my presentation?
Yes.
It is buggy.
Yes, Professor. Yes.
It is a little buggy. I'll try to open it again. Okay, so welcome guys. So we are going to develop a new property package for DWSIM today. We will use the same tools as that we used in the previous session. For those who are not familiar with the term property package, a property package is an object which contains a set of methods and procedures to calculate phase equilibria, phase properties, as well as pure compound properties. Okay, so we can have multiple phases, vapor, liquid 1, liquid 2, as many liquid phases as we want to support, one solid, mostly. This comes from the KP Open standard. I didn't put it above, but it is also from the KP Open standard. Also, some phase properties that can be calculated includes density, viscosity, thermal conductivity, compressibility factor, entropy, heat capacity, and so on. And some pure compound properties that a property package can calculate includes the boiling point at a specified pressure, the ideal gas heat capacity, which is a function of temperature, liquid density 2, liquid viscosity. These are all for the pure compound only. Enthalpy of vaporization, which is also a function of temperature. So this is just for you to get an idea what a property package does in a simulator. Okay, and today we are going to code the Wilson activity coefficient model. We will develop a property package which uses the Wilson model to calculate liquid phase fugacities, which can be calculated through the activity coefficients. The vapor phase fugacities can be calculated by Payne-Hobson equation of state, or ideal fugacities equal to 1. And liquid phase enthalpy, entropy, and heat capacity will be calculated ideally using a excess function based on the activity coefficients. I'm going to show you how this is done, or using the Lee-Kessler model, which is the default selections for all activity coefficient property packages in the DWSIM. Okay, and the remaining properties will be calculated by the default methods and procedures which are set in the base property package class in the DWSIM. Okay, so these are almost the same steps as in the previous section. We will create a new Visual Basic class library, add references to the Thermodynamics library, create a new class inheriting from this one, which is the base class for all activity coefficient property packages. I've created a skeleton, so you don't have to code all functions repeatedly again. You don't need to do that. You only need to implement a few methods. We will create a new class that implements this interface. This interface defines 3 functions: one to calculate the activity coefficients, another to calculate the excess entropy, and another which calculates the heat capacity, I think. I'm not sure, but we can check that. We will debug this library, and if we have time, I can create the editor for the property package so we can change the Wilson binary interaction parameters, and then we can proceed to the final tests. Okay, so let's see how the equation for the Wilson activity coefficients looks like. Let me try to open the Are you still seeing the screen?
Yes, we do.
Okay.
Yes.
Okay,
Yes, yes.
so this is the equation for,
Yes.
let me change the color of the pen. Okay. This is the equation for the Wilson activity coefficients. We will use this one because it is for multi-component mixtures. We can't use this one because this one is for binary mixtures, but in the DWSIM we must be as general as possible. Okay, so we will use this equation, and this is the binary interaction parameter, which uses this equation. These are the molar volumes of the two compounds, and this parameter is based on experimental data. Okay. When I was checking the equation, I thought that we would have to use temperature-dependent molar volumes, but here I found that in this footnote that we can use a constant molar volume independent of temperature. So that's what we are going to do. Okay. Well, let's go. So let's create a new Visual Basic process. Visual Basic project. Here we can use it has a file for Wilson BIPs, so we can use it. You can find, this is the concept directory. You have a folder called IPD. This IPD folder contains a lot of binary interaction parameters for different models. We have one here for Wilson model. If you open the file, you will see that we have a cast number for the first component, and for the second, we have the A12 value and the A21 value here. This is for acetone and water. We will read this file into our property package to get the values of the parameters. I've already formatted this file into some easier way, so we can read this file directly in DWSIM. Okay. So let's go class library, Visual Basic, and Net Framework. Okay. Okay, first thing is to add a reference to Thermodynamics DLL, so we can get the classes from it. We don't need to copy it. I'm going to set copy local to false. Otherwise, this DLL would be copied again. So, but since it is already there in the DWSIM's installation directory. We don't need to copy it again. Our first class will be our property package itself. This class will inherit from the ActivityCoefficientProperty Package base class. And this class already has everything we need except for one function that we need to override. You can see that this class that we are inheriting from already inherits from property package, which is a big file, big text file. So imagine that if we would implement all of this over again, look the number of lines in this property package class is huge. So what this activity coefficient property package class has. It has some default methods to calculate the phase properties. As I said, the vapor phase properties are calculated by Payne-Robinson, or ideally, if you have a selection for that in the property package editor, and the fugacity coefficient function for liquid phase. It checks if you want to use the pointing correction factor and calculates it here. If you have a supercritical compound, it calculates the fugacity using the Henry constant for that compound. Otherwise, it uses the value of the activity coefficient, multiplies by the vapor pressure, divides by the pressure, and then we have the fugacity coefficient for that compound in the mixture. If we have a ideal vapor phase, according to our selection, we use a fugacity coefficient equal to 1 and this logarithm equal to 0. Otherwise, we calculate the fugacity coefficient using the Payne-Robinson equation of state. Okay, so that's what this function does. The phase properties are calculating using the same default methods as the other property packages in the DWSIM. The liquid density depends on your selection. If you are using experimental data from the compound or using a equation of state. Enthalpy and entropy depends on the model and the option that we choose. The compressibility factor is calculated using the Lee-Kessler model. What else? The thermal conductivity is calculated using the default method. The liquid viscosity too. And that's it. In the enthalpy calculation method, we have 3 options for the liquid phase. If we choose the Lee-Kessler method, the enthalpy is calculated directly using the Lee-Kessler model. Let me show it to you. If we have the ideal option for the liquid phase, the enthalpy is calculated. Using a ideal term, which is the HID plus pressure divided by liquid density.
Then yeah, the writing is not showing up with the pen.
No? Okay.
No.
Yeah, I know what happened. I need to switch to the whole screen.
Yeah.
Mm-hmm. So, is it showing?
Yeah, that's.
I'm going
Well,
to. I'm going to write it again.
Yeah, it was showing.
Mm-hmm. So we have. Okay. I need to learn how to use it. H equal to. This is for the liquid phase. The reference state for the DWSIM is ideal gas at 25 degrees Celsius. So we have the ideal term plus pressure divided by density minus the enthalpy of vaporization for the liquid phase. If we have the option for excess, we selected the excess enthalpy calculation mode, we also need to include an additional term, Hx, which is calculated using the activity coefficients. And if we have the option for the experimental liquid, for some compounds, for instance, for ChemSep compounds, we have data for liquid heat capacity, so we can use this data to calculate the liquid phase enthalpy using this equation plus the density term. Okay. What we are going to do is to find a way of calculating this term, the excess enthalpy term, because the other ones do not depend on the activity coefficient models. The entropy is the same, it just has some different terms, but it's the same philosophy. Okay, so let's go back to our method. We need to implement the new function. This new routine from the base class asks if this property package will be using the KP open mode or not. By default, we are going to use it for the DWSIM only, so I set this parameter to false. Another method that we need to override is the getArguments function, where we need to return the arguments for the Wilson equation, but we are going to do this later. We need to add now a new class for our Wilson model itself, so we can calculate the activity coefficients in here. And this class will implement the Thermodynamics property package, auxiliary, activity coefficient based interface. So this one asks for the activity coefficients, the excess enthalpy for that enthalpy calculation mode. This is where it comes from. And the excess heat capacity which I believe is not used anywhere, but we will do it anyway. I'm going to add the file with those parameters for Wilson model. This is a CSV file. We are going to set it as a embedded resource, and we need to create a dictionary for our class here, so we can store the BIPs in memory. We'll create a new dictionary for that. BIPs as dictionary of string. Then we have a double array. This array will contain two elements. The first element is A12, the second one is A21. Okay. Am I missing? Yeah. I'm going to put a comment here. First key is compiled in SID. Second key is compiled in SID. Value is a proper array containing calories per mole. We will implement the initializer for this class, and here we need to read that file. I'm going to do some copy and paste here from Angular because I don't remember how exactly we are going to read it. We need to initialize our collection. With this command, we will load the CSV file in memory and read its contents. I think we need to be careful with the path of this file. We must enter the full path here. Thermodynamics. I think it doesn't work always like this. Visual Basic and C# handle this differently. I hope this works, but we can test this later. Here I'm going to load contents, read the contents of the file. Here read one. This will read the entire file and store it in this string variable. And now I'm going to read the file for I equal to 1, because we are not reading the first line. first line has a 0 index, so we start from 1 to, I'm going to use another variable here, file lines, file contents, split. We will split this string by the new line character. Count -1. And so we have the cast ID1 equal to file lines split by semicolon, semicolon, this first element in this line, second line is the key cast ID2, A1, 2, file lines. There are other smarter ways of doing this. I'm just doing this because it is more didactic, I think. Didactic ou didática? Didático em português. Okay, now these are all strings, so we must, these two parameters are strings really, but this one is a number and this one is a number. A number formatted using .s decimal separator, so we need to convert it to double parse the string using globalization system culture info invariant culture, so it can read the number decimal separator right here. Okay, and now we add first we need to check if our VIPs contains, if we have the first cast ID on our collection, then we check if this element contains the second cast ID, then we can add, this will not happen, but I'm just putting as a safeguard, equals to new double and otherwise we will add a new element, new double, into H1. If we don't have any of this, so we must create a new dictionary, one, new dictionary, and then we can add the second. We can paste this one. Okay, so this way we make sure that we don't have repeated items in our collection. There must be a case where we have a inverted order of the compounds, but we have this BIP in the collection, but with inverted CAS IDs. So we must make sure that we don't miss this BIP for this pair. For instance, if we ask for the ethanol water BIPs, we have it here, but if we ask for water and ethanol, it can't find it because they are in different orders. So we must make sure that we also do this for the inverted order of the BIP. So we must make sure that we have CAS2, CAS2, CAS1. No, I'm not going to do this. There is a better way of doing it later. Let's implement a function. This function get BIP CAS1, CAS3, CAS2, as double. So we check if BIPs contains key CAS1, then if BIPs CAS1 contains key CAS2, then return BIPs CAS1 CAS2. Else, in this case, we can have a inverted BIP set, so we can just ask if instead of having CAS1, it may have CAS2. So we proceed with BIPs CAS2 contains CAS1. Then we have a new BIP. We must return a inverted BIPs because the order matters here. We must switch the position of the vector. Let me know how I can do it. We can do CAS2, CAS1. No, there is no. Do it the hard way. Yeah, so if we have the CAS1, then we check we have CAS2 in CAS1 collection and return the BIPs. Otherwise, if we don't have CAS2 on CAS1, we check if we have CAS1 in CAS2 and return the inverted set. Otherwise, we return 0. If we don't have CAS1, we check if we have CAS2. Then if we have CAS2, we check if we have CAS1 inside CAS2. Return the inverted set. Otherwise, we return 0. That's it. Are we missing something? Yes, this one. Okay. I'm going to compile it just to see I need to go here and we are going to create a some model as Wilson. I need to put another name. This one M. Here we initialize the Wilson name. Equal to new Wilson model. I think I need to put this after. Yes. I'm going to test if we are reading the file correctly. Okay, just for start. I'm going to compile the library. And copy it to the installation directory, ppax folder. If this folder doesn't exist, you can create it. Okay. And I'm going to start DWSIM. Oops, index was outside the bound of the radius and not allowed to it didn't work. 9:30. I think that it is not splitting the lines correctly, and I believe it is better to use a lines list of name, and then lines add to read line. Yes, this is better. Because there are some issues with the new line character on some files. For each lines.
That is came from the Linux Windows thing, or it's common?
Sorry?
I say this end of line issue came from the Linux Windows issue?
Yes, we have. Yeah, sometimes because we have different in Visual Basic, we have different characters for line endings. We have VB, CR line. We have VBCR and VBR. Sometimes you need to use both. You need to use all of them. Sometimes only one works. But in the end, you end up with some blank lines in between. So it is very probably, it depends on the text file, which character was used to represent the line ending. Line. I'd like to start the DWSIM. directly from here. I think I can't. Another one. Oh, I didn't compile the file. I need to compile it. We can't debug this step because the DWSIM tries to initialize the variables right at the start of the starting procedure. But if it doesn't show any errors, we know that everything went okay. Still we have 31. Input string was not equal to oh, because I'm trying to read. I'm going to remove this line here because we know already what it means. Oops. Add products. 9, 6, 7. Oh, okay. I need to define the name of the property package. Need to component name. Some description. Yes, so hopefully we can see it on the property package selection screen. Yes, we have it here already, but it's not working yet. We can proceed to the actual model itself, the equation. The DWSIM passes the temperature in Kelvin. Kelvin. Dx is the liquid phase composition, molar composition. And other arcs can include anything. Other arcs. We saw that we need at least, to calculate the activity coefficients, we need the binary parameters and molar volumes for each compound on the mixture, right? So we need to know the Cas IDs of the compounds, so we get the BIPs from that function that we created, and also the molar volumes for the compounds in the mixture. So we will actually put the first element in this object equal to the gas IDs, and the second element equal to the molar volume for each compound. So we can do this thing, gas IDs, with the other arms as gas IDs as string, other arms 0, and V molar volume as double, with the other arms 1. Okay. Now we go back to the Wilson property package, and we must return the gas IDs from these functions. We can get it by using a auxiliary function. Read vcas. This function is a helper function in the property package base class. Let me show you. Here it is. Since this function is in the base class, we can access it from any class that inherits from it. And this function returns simply the gas IDs for all the compounds in the mixture, in the current material stream associated with the property package. And to get the molar volumes, I'm not sure if I have a helper function for that. No, I don't. What do you suggest we do here? We can calculate the liquid volume for each compound. Let me copy the function from here. So we always have a material stream associated with the. We must add a reference to interfaces. Okay. He's asking for DWSIM interfaces. Okay. We can calculate the liquid density of this. This will calculate the liquid density for each compound. No, we will need to use the same temperature as the one that we are going to use to calculate the temperature, and we must figure out how to do this. Let me see if I have something. Standard state molar volume. I'm not sure if this property is read from concept compounds. Otherwise, we could use it. For now, let's calculate the liquid density at 29.8 Kelvin. Just so we can proceed, we can figure out a way of getting the correct values later. But since here we need the molar volumes, which is, I believe, is moles per cubic meter. This one comes in kilogram per meter. We must divide it by the molar weight, right? Are you there? Or? Yeah. Are you still there?
Yep, we do.
Okay.
Yeah.
Is this correct?
Yeah,
Is this correct?
I'm trying to write something.
Mm. Here we need we have kilogram per meter divided by okay. That's okay. So we must actually we will not return val, but we must return a new object. And the first element is the gas IDs array, and the second one is the molar volumes. Okay, I think this is enough. Now back to the activity coefficient calculation. We need to calculate minus L and some jump. We need to calculate the binaries first. Okay. Need to define a new What is the name of that letter, Greek letter? Do you guys know? What is the name of this letter? It's down. Greek.
I don't know.
Oh.
It's not a lambda. Okay, it is.
Lambda.
Yes, lambda.
Yeah, lambda.
Yeah.
It's the same. The number of compounds we have is the same length of the Vx vector. We will need a I, J, and equal to Vx. So y equal to 0 to I'm going to put -1 here, so we don't have to put -1 elsewhere. Okay. Our lambda is molar volume J divided by I exclamation molar volume J divided by molar volume I times math minus get the no here yeah the BIP guess what guess is I know what we need here. Since this BIP is in calorie per mole, we need to divide it by okay, 1.9872. And our lambda J Y J I know this is a little confusing, but I had a lot of experience with this using coding unifac and modified unifac, and this is much worse than this, believe me. These indexes get me crazy. Okay, now we will calculate the first sum. We need sum J X J and I J. This one is sum 1. Y equal to N. Sum N to 0. Sum plus equal to X J tau lambda times lambda J If you guys don't agree with me, you can just stop me because there will be probably something wrong with the two correct later. I don't think we will need this, but let's go on, see if this is correct. The second term involves two sums. You will need to do this sum first. Sum J. Sum, I'm going to call this sum 2, which will be a K sum. It will be the same. It will look like the first sum, but we will use it for the K index. I'm going to copy and paste it here. So, 2. And sum 3. Sum 3. Let's declare the K variable just to make it more, make it easier to learn. This one will be xk divided. No, we need that. We need the second one. Y, and then this ki. No, I think this is not correct. This is based upon the y index. I. This is actually some. Line. Okay. That's good. Okay, y. Divided by some 2. Okay, I think. So now to the activity coefficient. L and equals to minus some plus 1 minus some 2 y. And active coefficient equals to the exponential of then we return active. Okay, so that's probably the I'm not sure if this is correct, but shouldn't be very different from what I've wrote. We will probably need to correct something here, I'm not sure, but only during the test we will know. Okay, now to calculate the excess enthalpy, we remember that the excess enthalpy is a function of the activity coefficients that we have here. So we need to calculate HA, which is equal to, if we multiply that this to here, we will have minus Q T and okay, so this is the equation, and we can use that previous function to calculate the numerical derivative for this one. So let's proceed with this calculation. We can define our first gamma of activity coefficients using the current temperature minus 0.01, just for a small perturbation. Gamma 2 temperature plus.
Just a question right here, because one of the guys was asking about mathematics. First, the question is, there is not a way of computing the derivative in an analytic way. This is the first question. And the second question is, I see in all your software that you always use absolute values instead of relative values. In this case, you are using centered numerical derivatives, but sometimes you use forward numerical derivatives.
Yeah,
I think that for stability.
Yes, we could use the analytical derivative, but I don't know. I didn't find any reference for it in the Wilson equation. So this one is faster, and we can learn from it this way because it is easier. But we can change it later. You can write your own derivative. You can use a math library to write.
No, I say this comment is in a general way for the complete WSIM software.
Yes, you can do. Obviously, the best way is to use the analytical derivative. But let's just try to produce a value here, a reasonable value for us to analyze the impact of this excess enthalpy into the temperature of a mixture of water and ethanol, for instance. I'm planning to do that as we test our library. So we have Ajax equal to minus 8.3 plus times. Oh, we need to do this here. I'm just going. We need to return this in kilojoules per kilogram. I'm going just to check if we are doing this here correctly. Oh no, we must return it in kilojoules per kilomole. Okay, so we don't need to do any further conversion here. The excess heat capacity is the derivative of the excess enthalpy with respect to temperature. I have a ready to paste code from here. I just need to change it from cap to access. I'm going to use a centered derivative here. I think we're okay. Let us see if we are calculating everything correctly. The BIPs are being read correctly. We will try a water and ethanol mixture because I know we have a BIP for this mixture. I'm going to save it. I'm going to attach our project to debug the running code. As soon as we drag a new stream to the flowsheet, the DWSIM already tries to calculate it, so we will see a calculation try right here. Okay, we will check if we are returning the CAS IDs correctly. Okay, molar volumes. Okay, both, I believe. Now it should enter this function to calculate the activity coefficients. No, it didn't work. Maybe I have forgot something. I think it is this function that needs to be implemented. this one is to check if we have a BIP. If for this given mixture we don't have a BIP for any binary, and this can compromise the result, so we can return a error message here just to warn the user that a BIP is missing, but let's always return true here just for the sake of testing our library. Oh. Open the wrong simulation. Strange, what are we missing? He's complaining about something in this line, but okay. Okay. I forgot to override the function that returns the Wilson model. Overrides. Okay. Let's put this to the top. Overrides. We need to override the get model functions, which will return our Wilson model. So the base property package can call it and call its activity calculation method, activity coefficient calculation method. That's what was missing. I think that we also missed something for the name of the property package. Probably not. That's good. Oh. Again. Let's see what's going on. Yes, I need to set this variable to our model class instance. Okay, now we are inside the activity calculation routine. These are the molar fractions for water and ethanol. Temperature, the arguments are here, the cast numbers, and the molar volumes. So let's see. Let's see if we have the BIPs. Oops, we only read one pair. I forgot. While I forgot to ask to read all lines until we reach the end of the string. Let me just check if I'm forgetting about something in the property package. I think that the DWSIM isn't ready to load property package based on that activity coefficient base class from external libraries. I need to fix this, but For now, we will have to add the Wilson property package every time we load the simulation, okay? But I'll fix this in the next version. It seems that it is calculating, but let us try it again. Okay, so we have the BIPs. Now we have the full collection. For this specific case, we have the first case ID for water, 773264.75. 773, this one. I think it is this one, right?
Just a question, at which moment you are determining which phase you have in the...
Which what?
In the stream. Which phases you have, if you have vapor, liquid, or anything else?
No, it is back in... I'm not sure we'll be able to see it here. You can see that it goes straight. We have the call stack here. We have the calculate function for the material stream. Then we have the calculate equilibrium. And then we have the flash algorithm. And inside the flash algorithm, we ask for the K value. And during the K...
Yeah, just a question. We have changed somewhere else. Is there a way that you can actually bypass all this step and force the phase to be something that you decide at the very beginning? When I say the, it's been
no,
in many cases.
No,
in many cases, I'm not talking about the particular case that we were discussing before. But just for example, when you have a separator and you are using plant data, any deviation, this means you have a set of pressure and temperature, and any you can be 50% of the time as vapor when actually you are liquid, and the opposite, you can be liquid, and I don't know if you get my idea. This means, for example, any sensor, if you have saturated stream with water steam, you have a separator at the top is vapor, at the bottom is liquid, and both have the same temperature, the same pressure, by definition.
Yes.
So it's at the given moment you need to specify what you are getting in one or the other. This is easy when you are in simulate in design, because you by default you say what you have at each stream.
Yes.
But when you are using plant sensors, you have maybe at the bottom 1 degree more than what is expected at the equilibrium, and then you are flushing the stream with actually in practice liquids, just because the error came from the sensor and not from your model. This is a very, very common situation when you do RTO, real-time optimization, because you need to use plant data that contain errors, and it means it will be interesting if we can bypass this test, saying, hey, don't test this liquid because I know that it's liquid, because it's at the bottom of the equipment, and use the temperature, even if it's overheated liquid, I don't care, because it's what it is. You know, sometimes the thermodynamics contains errors, by the way, and maybe it's underestimating the temperature, and the actual plant temperature is just a little bit higher. And this is also very common when you have air inside the vapor stream. When you're dealing with water, use pure water. It's IPWBA 97, the thermodynamics, but this works very well for pure water. But when you have some air, some nitrogen, something with, your equilibrium is not anymore the same, and it's not your data that is wrong; it's your model. But by the way, what you have. And this I find that this limitation is very good in design, but it's a drawback when you're dealing with real data.
Yeah, you cannot do it directly, but you can use some Python scripts to force or bypass the equilibrium calculation, or force the fluid to be into a single phase. It is possible to do, but you have to write a script to do that, because you can associate a Python script to the calculation routine. You can either run it before the calculation begins or after the calculation finishes. So you can link your script with a specific event during the calculation, and you can do what you want in this script. Because I believe that you won't need to do this for every.
No, I'm not
block.
expecting you to do any.
Yeah, just for the separator, for instance, you would need this for specific sensors. So I believe it is possible to do if you. Because it depends on what exactly you need. So if you need everything to be in liquid, we can get the composition of the inlet stream and force it to the liquid phase and do not calculate the equilibrium. This is possible to do, but you have to write your own script to force this.
Okay, no, because my idea with some other softwares, by the way, with the Aveva, you can do it quite easily. You can specify the phase. You say this is liquid, and you can specify this at the stream itself. You know, at the stream, you are not letting it to be whatever it is based on your thermodynamics, but you say, hey, whatever it comes, because we are dealing with RTO, with Romeo, you heard about, whatever it came, you compute a liquid phase. By the way, you know, sometimes you compute in your source, but you're computing strict equilibriums. That's nice, but sometimes
you don't always need that. I know. I got it.
So when you have a separator, you're not at equilibrium. By the way, you have some mixing volume. That is what it is, and then you start splitting, and you have some units operations that have deviation from the equilibrium. This means you can call it efficiency, and there are many ways of modeling something that is not exactly the equilibrium. And it means you work in oil and gas, and you know that the equilibrium for a vessel is almost never reached. You have 1% of the equilibrium, so your software is doing too well for representing the actual plant.
Yes, but that's a good idea. I think it is easy to add a property into the stream to force it to be a single phase or a percentage of the equilibrium phase distribution. I think that this is possible and easy to do.
Okay, yeah, that's it. This is why I'm asking, you know, because it's very simple. You just bypass equilibrium, you say that it's liquid, you go to compute your CP, CP delta T plus residual properties and so on, excess properties, sorry. And yeah, it's much odd, because computing the equilibrium, then bypassing the equilibrium and so on, you end up with a complex solution.
So can you create a feature request in GitHub, please?
Yeah, of course. I mean, I just discussing it with you because we are creating this unit operation right now.
Yeah.
And
I think we can do it in the following days.
It's very practical.
That would be nice. So let me.
Because this is the real subject today. You know, it's the thermodynamics and how good or bad they can represent our system.
I agree. So. Let's move on here with our calculation check. It is calculating some reasonable values here, right? But I don't know if they are wrong or right. I'm not sure if we got the sums right here. But we have a way of checking if we are calculating it correctly or not. We can add, for instance, a UniQuack property package. And we can set it to UniQuack here. I think, yes, we have, for instance, for UniQuack, we have these values for the activity coefficients. And for the Wilson model, we have this. I probably got something wrong, but we can.
No, they're pretty much the same.
No, they are a little bit different. Oh, look.
They are 140 and then
Yeah,
points
the other is 1.0. But let us check in a binary envelope. Using the unique model and Wilson model. Yeah, it's not quite there, but if we compare the models, we have. Honestly, I don't know if this is what we would expect from the Wilson model. I'm not sure if.
Yeah, I know that's surprising. You know, sometimes you have really this kind of difference between one and the other.
Yeah, I'm not sure if this is what we would expect, but I think that we are going to waste too much time trying to figure out what's wrong. I can do this later after the session, and then I will upload the code to GitHub, and if something's need correction, I can fix it later. So we don't waste much time trying to. You don't have to wait for me to find the error because it can take hours or days. This happened before, believe me.
Testing for every possible combination of components and so on.
These sums in these activity coefficient models are really difficult to get right. If you look at the NRTL model, they have a lot of sums of sums, and this gets me crazy every time.
Yeah.
If you see here, for instance, the calculation of, you have a lot of sums, and this, if you get a index wrong, you will mess all the sums at once. So.
Do you have some kind of automatic test for validating thermodynamics?
No.
Or just
no, I just
you
go right. Okay, okay. Next step is to. I think we didn't create the editor for it. But the property package settings, you can select the method for the calculation of enthalpy. Entropy by default is Lee-Kessler, but I would like to check if we are calculating the excess enthalpy correctly, so we can actually see what is the effect of the excess enthalpy in the temperature of mixing of water and ethanol. Let me just create a simple editor here for our property package. Let me just see how I did in the Uniquac. Okay. I'm going to create a new form. This editor will have a public property package, and we will add a control. That panel to edit the property package settings is already done here in the DWSIM. I'm going just to add this user control to our editor so we can set all its properties using the existing control. auto scroll through. Okay, and here in the property package, I will define the editable. Okay. What is the property name? Okay, it's configurable. Me should be deprecated. It's ugly. Now I'm going to override display editing form. And here I will FAC use some editor which is found to be customary. And then add show. This will display the editor for use on. I'm going to mix water, pure water with pure ethanol here, so we can analyze the effect of the enthalpy calculation method into the outlet temperature. Oh, I forgot to. By default, we use the Lee-Kessler enthalpy calculation method. You can see that there is a difference here in the outlet temperature, but this one is calculated by Lee-Kessler. So let us debug the and we'll go back to our excess heat capacity function. Excess enthalpy, sorry. So we have 291 Kelvin. Okay, and if we switch to ideal, we have almost the same temperature. We don't have any mixing effects as expected. We also have an option to use experimental data. This experimental data, let's go back to the activity coefficient page. The difference between ideal and experimental data uses the liquid heat capacity instead of using the ideal gas heat capacity and removing the enthalpy of vaporization. We use the liquid CP directly. So let us see what happens. No mixing effects as expected because we don't have any mixing effect here. We're only using the individual liquid CPs here, so we don't have any mixing effect. We should have something here because we are explicitly calling the excess enthalpy calculation from our Wilson model here. And once we change the calculation mode here to access properties, we should get something here, which is 0. Oh my god, this is unexpected. 1.5. No, this is wrong. Oh no. Okay, this is calculating the excess enthalpy for the pure water stream, so the excess enthalpy is 0. And the same. Let us see if the composition changes. Okay, now this is the mixed stream, and then we have our enthalpy of mixing here, the excess enthalpy. And this will have an impact in the final temperature because it changes the final enthalpy. So we have here our mixture actually heats when mixed. I'm not sure if this is the real behavior. Does anyone know? I'm not sure if when we mix water with ethanol the liquid heats or cools. But here we have a 6 Kelvin increase. And this
you're supposed to release some heat because they are polar molecules.
But this is really interesting because usually the authors of the papers that compile a list of the binary interaction parameters, they don't usually use the heat of mixing to fit the BIPs. They usually use only vapor liquid data. So the amount of heating or cooling does not represent the reality very well, except for modified. I think that, yes, I'm not sure if the NIST or Dortmund model, they use the enthalpy of mixing data to fit their parameters. So I think that these two models represent the reality better than Wilson, I guess. But it all depends on the values of the BIPs. If you use your data to fit a BIP exclusively for mixing, heat of mixing, then you would have got something closer to reality in this experiment. But it depends on the model and on the BIPs mostly.
Let's say that you are not modeling the heat, but still
you
can see it from the equilibrium.
Yeah, I'm
you come
sure
back to it.
You can see that we are calculating the heat of mixing from the activity coefficients, right? We are using the values to calculate heat of mixing. You can, if you look at the papers for the modified UNIFAC, for instance, they explicitly tells that the original UNIFAC method was not created to represent heat of mixing because they didn't fit the parameters to using data from mixing effects. They only used vapor liquid equilibrium data. But in the modified UNIFAC, I'm not sure if it's Dortmund or NIST, they included the heat of mixing effect, so the parameters already capture this effect. So theoretically, they should give you better results here in this mixing. But that's only what's written on the papers. I'm not sure if this is actually what happens here. You see, this one cools the mixture. This is really weird. So it depends on the parameters that you have. Parameters. I personally, I do not recommend using this calculation mode only for educational purposes, because sometimes it can give you really weird results. I prefer using Lee Kessler or Ideal. By default, it is using Lee Kessler. Okay, that's it. I'm going to check if these equations are correct, and then I will upload this code to GitHub and add this property package to the DWSIM in the next version. Okay, so that's it. If you have any questions or suggestions, what you want to see in the next session, I'm open to suggestions. Okay.
Thanks, Daniel.
Thanks,
great.
Daniel. I have a request, Daniel. Could you, in one of the following sessions, work in an utility?
Yes. Oh, okay. I forgot about it.
Yeah, I told you last time. So anytime.
Okay.
I mean,
Let me,
not in a hurry. Whenever you have the opportunity.
Let me take a note here.
What you call an utility?
It is a plugin.
Okay, a plugin.
Yeah, something.
Actually, doing plugin is not that hard. You take some examples from what I did some of them. They are listed from 1 to 6. I don't know. Maybe Daniel can explain you why. But still, you have some. Depends. Some ones have some functionalities. Some others are either different. But still, they're not that hard if you take an example.
Yeah,
it's quite straightforward.
I'm looking for a modification of the proper petroleum properties. I'm looking for the 95% distillation of ASTM D86. So in order to calculate back from the composition of the stream, calculate back the property of the ASTM curve. So that is the utility I'm interested to do. So any skeleton that may help would be great. Or either you can initiate for doing something like that, and I can try to keep working on that.
Jose, can you send me an email with the details so we can, for instance, we can get the mathematical equations before starting our session, so we don't waste much time trying to figure out the calculation. If you give me an overall idea of what you want, I can think about it before the session, and we can proceed without wasting too much time the next time.
Yes, I will investigate a little bit about how can that calculation be done. And
then
I will forward to you an spreadsheet or whatever visual basic skeleton.
Yeah, we have the methods already in the DWSIM. So, for instance, if you want to generate the assay from the stream data, we can calculate everything backwards. Instead of generating the pseudo compounds, we can generate the curve from the compounds from the stream data. I'm not sure if this is what you're asking for.
Yes, that is what I'm asking for. Actually. Maybe it is okay.
And you let me know exactly what you need, which methods do you want, so I can go straight to it. And
okay, I will forward to you an email with that information.
Okay, thanks.
Yeah, it's interesting. I'm interested also in that calculation, back calculation actually.
Yes,
because when you are trying to, and also if that property, utility calculated property can be used in a spreadsheet for setting a value, because When we try to work in a distillation tower, oil distillation tower, as you know, we have to maintain several specifications. So sometimes it's very useful go by the 95% of the string or 90% of the gas oil or whatever. So having that accessible, that property first calculated and accessible in a spreadsheet or an specification is very helpful. So that is the idea. Okay. Okay, thank you. Thanks a lot for your...
Okay. Thanks,
Okay.
Daniel.
Thank you guys. Thank you for watching. I'm going to upload this video to YouTube later today. Okay. Thank you very much.
Okay. Thank you.
And see you next time. Bye bye. Take care.
Bye.
Bye-bye.
Nice
Stay
weekend.
safe.
Have a nice weekend. Bye-bye.
You too. Bye bye.
Daniel, sorry, you mentioned that we may make suggestions. I know it's a very small suggestion from my part. With short experience in Aspen with DWSIM and programming in Python, most of the mistakes we commit when we are doing an iterative mathematical process come from the mathematics itself. I remember that the mistake came from the line 593. Is that correct? And that line was inside of an iteration. Maybe the mistake itself was in the line 590, I don't know, but right at the beginning of the iterative process, not the mathematics itself, because I clearly saw that you wrote correctly the mathematical equation of the Wilson state. Yeah. So it's just a small suggestion. You mentioned that you desire to check out that later. It's my small suggestion. Sorry, but
No, so can you say it again, Gustavo? You can speak in Spanish if you want. I can understand Spanish if you speak slow.
I strongly need to practice my English.
Okay.
Yes, my only suggestion was to check out the lines above line 593 because I think the mistake is at the iterative process order, not at the mathematical equations.
Oh, yes.
Because I clearly saw that you typed correctly everything in the mathematical order. Sometimes, if you think about it, maybe, just maybe a little bit more lines of code may be better, just to specify that, or how to say it, some compounds, some sumatories are a single variable, and you calculate it right directly to divide it. You specified one time that the function square of something is more accurate than doing directly the square of something. Maybe that's a small mistake we committed. That's it. That's okay. Small suggestion. Sorry.
Okay, thanks. Thank you, Gustavo.
Yeah, I'm just about to receive my chemical engineering degree. I apologize for my lack of experience, and I came here for that to receive a little bit more of experience.
No, that's okay. We are all learning here. Don't worry. Okay.
So, that's all for me. Thanks all for the course. I enjoyed it a lot. I need to swing out. It's already a little
Okay,
bit
Gustavo.
late.
Muito obrigado.
Thanks.
Obrigado. Tchau, tchau.
Muito obrigado.
Tchau,
Adiós,
José.
Gustavo.
Obrigado.
Adiós, Daniel.
Adiós.
Bye-bye.
Hasta luego.
Hasta luego.